Okay, so now we start a topic for today, which is basically artificial neural networks. So as I told you, this is actually a topic that you see towards the end of a course on machine learning, right? So where your course contents of machine learning and this course actually starts from there, okay? But just to make sure that all of us have the same prerequisite knowledge of ANN and perceptrons. So I told you that I'll give you a quick recap of ANN along with an implementation guide and a numerical derivation of how neural networks learn. Okay, and your first assignment would also be based on the same topic, that is ANN. Okay, so let's dive into more details and see what are ANNs and how they work. Okay, so I'll be skipping some low level details, right? I cannot completely cover it because otherwise it will take 3 to 4 weeks. So we have to conclude it, or at least the major proportion of this today. Okay, so the low level details which are related to ANNs, I'll be skipping them and I'll be focusing more on abstract layer details. Okay, so basically in this discussion, we'll see what are neural networks. We'll first start with the simplest possible, you can say, neuron, which is a single neuron that is called perceptron, and we'll see how it learns. Then we'll move on to a multi-layer perceptron where you have different layers between input and output, right? And then maybe towards the end, I'll give you some idea of backpropagation. I think it would be difficult to cover it today, but the implementation guideline, a small piece of code that is implementing neural networks, and that I'll show you today. Okay, so basically if we try and explain what is a neural network, right? So the simplest or a crude way of defining an ANN is that it is a computer program which is trying to simulate human brain, right? This is the simplest and the most, you can say, crude way of telling what a ANN is, right? And if we go deeper into the details, so you must be knowing that human nervous system comprises of billions of neurons which are connected with other neurons, right? This is basically a biological neuron, which is the unit of central nervous system. So you see, if this is a cell, so in the center you see something which is called cell body, right? And then you have these branches which are connected to the cell body. So the neuron or the cell body is receiving some input on these branches, right? And these are actually coming from some other neuron. So this part is doing some processing, and then it is giving output on this branch. And this branch itself could be connected to many other neurons in your brain, right? So this is the general idea of how a biological neuron looks like and how it receives input. It will do some processing and then it will propagate forward the output. Now, inspired by the same idea, if we now talk of a digital neuron, so what do we have? We have basically this block which you can correlate with the cell body, right? So it is receiving input from multiple channels, right? Maybe some input here, and so on. And every input is multiplied by some weight, okay? And then they actually come to this cell body, and what this cell body is doing, maybe we see here. So the cell body is actually taking a dot product, right? What is it doing? It is simply multiplying the every input by the respective weight and then adding them together, right? So if you see this expression, the expanded form of this expression is here, okay, where you have the first input, which is x1 multiplied by the corresponding weight, similarly x2 multiplied by the corresponding weight, and so on. So you add them together and you can actually write them in a compact form using this summation notation, right? Okay, so this is one thing that the neuron is doing, but that's not all. There's another thing that we do, which is called application of an activation function, right? So if you compare this part with the cell body, so within the cell body, there are two operations that are being performed. First is you are multiplying weights with input, right? I come back to this later. And then you are applying some function, some activation function, right? I'll show you in a while what are the different activation functions available. But let's now discuss what is this, okay? So in addition to the inputs, we also have another, you can say, a special input, right? Where you don't provide any input from the outside, you wire it to 1, you fix it to 1, right? And the weight of this edge, it is called a bias, right? So bias is also a parameter which is learned just like these weights W1, W2, and so on, right? But it does not have any specific input that's coming from data. or you can assume that the input is constantly wired to 1. So that's why 1 into bias is actually bias. So that's why you don't see any coefficient with this parameter. Okay. So what we are doing, we are multiplying weights with input, adding bias, and whatever we get here, we just apply some function on it, right? And that function in the context of ANN is called an activation function. So now if we see some conventional activation functions, I'm sure you must have seen these earlier. So the simplest one is the step function, right? Step function, what does it mean? That it will give you only two outputs, 0 and 1. Okay, so you can say, okay, if my value is greater than 0, the output is 1. Okay, for all the values greater positive values, the output is 1. For all the negative values, the output is 0. A very similar function is called sine function, where again you have only two possible outputs, but instead of a +1 and 0, now you have a +1 and a -1. Okay, so they are pretty much the same thing. The only difference is that on the left side you have 1 and 0, here you have 1 and -1. Then we already discussed in detail the sigmoid function, which is a very common function that we'll often see when we are talking about neural networks, right? And then a less common function, which is a linear function, is that whatever is the input, you just give it as an output, right? So this is a straight line at 45 degrees. It means whatever is the input, say input is 5, so the output is also 5, right? So if I apply any activation function, the linear function simply gives me back the same value. Okay. Now you see, a sigmoid is, you can say, the most conventional activation function, which was very common in feed-forward networks. And then there's another variant, which is 10H, right? Similar to sigmoid, it will compress values between 0 and 1, and it will compress values between -1 and 1, and they have pretty much the same shape, right? But then these are some modern, you can say, activation functions, which you will often see when we are talking about convolutional neural networks, right? We'll see them maybe after a couple of weeks. But these are the activation functions, ReLU, leaky ReLU, exponential ReLU, and there are many other variants. So in conventional or traditional ANN, these are the common activation functions you will see. Okay, but with you can say the latest convolutional network, the common activation functions that you will see are ReLU or leaky ReLU or exponential ReLU, right? Okay, so with that preamble, now we are in a position to talk about perceptron, which is, you can say, the atom or the building block of unit of deep learning, right? So perceptron is actually one single neuron, right? There are no layers, nothing. You just have one neuron, and we want to discuss whether a single neuron can learn something, means can it represent something without any layers. Okay, so in order to understand the perceptron, we take this classical example. It's a good example that will illustrate how perceptron works, right? So it says that suppose at your workplace you daily visit cafeteria, right? And you get lunch, and your lunch every day comprises of these three items, right? You get some portions of fish, some portions of chips, and some portions of drink. Okay, and you don't know the prices of these individual items, right? So all you know is the total bill that you have to pay. Okay, so maybe this this is the price of fish, this is the price of chips, and this is the price of, you can say, drink, but you don't know these prices. X is the number of portions you order, right? So maybe 2 portions of fish, you don't know the price, plus 3 portions of chips, you don't know the price, and then maybe 4 drinks, but you don't know the price. Okay, all you know is the total price, whatever the cashier tells you. Okay, so now suppose you want to guess what could possibly be the prices of these three items. Okay, so these three prices are like the weights in a neural network. Okay, you can correlate them with the weights that I just showed you in the previous slides. Okay, okay, suppose these are the true prices of the items. Okay, so you can think of this single neuron as the brain of the cashier. That what is he doing? The cashier is doing, you order 2 portions of fish, and this is the price of fish. Okay, so what he will do? He will do 2 into 150. This is the same thing which was happening in case of, you can say, a neuron, right? Which I told you, input multiplied by weight. Then he will say, okay, you have 5 portions of chips. So he will do 5 into 50. And then he will say, okay, you have 3 portions of drinks. So 3 into 100. And then he will tell you the total price, which is 850. Okay. However, you don't know these prices. Okay, you just buy this and the cashier gives you the final amount, which is 850. So one day you think, okay, let's try and guess what could possibly be the prices of these items. So you start with a random guess and you say, okay, let's assume everything is the price of everything is like 50. Okay. And then you say, okay, if these are the prices, what would be my bill? So you do the same thing, 2 into 50 plus 5 into 50 plus 3 into 50, and you end up with 500. Okay, the actual bill was say 850, but your estimate is 500. So it means there is a difference of like 350 rupees, which is your error or residual. Okay, so you see this now, based on your observation, what will you do? Your estimate is less than what is the actual price, right? This is the actual price, 850, and this is your estimate actual. So you'll say, okay, I need to increase the price of something to go up. Okay, you will guess, of course. So maybe you will say, okay, instead of 50, let's make it 75. Instead of 50, let's make it 100, and so on. So you will keep on doing it, and you will try different combinations so that you arrive as close as possible to 850. So this is the general idea of how a perceptron learns. Okay, now you can think of these numbers not as prices of different items, rather the weights of a neuron. And these are your three inputs, x1, x2, and x3. So we are doing the same thing, x1 into w1 plus x2 into w2 plus x3 into w3. But the problem is that these weights, we don't know in advance. Okay, there has to be some learning algorithm that will help you learn what are these weights. And I just explained you a very crude way that how the weights can be learned, okay, just by guessing. But that is a very crude way. We'll see shortly what is the formal way through which we can learn these weights. Okay, so I think we just started, but it's time for prayer. So maybe we will have to take a pause here, right? And we'll resume after 15-20 minutes. Okay, it's about 6, so let's resume at 6:20. Okay, so I'm just pausing it. Okay, and then we'll resume. Okay, so now let's formally see what a perceptron is, right? So this is the same, you can say, concept which we have been discussing, but a more formal representation of how a perceptron looks like, right? So these, what you see here, x1, x2, and so on, right? So these are actually your inputs. They are multiplied by weight, and this is actually your bias, right? Which is connected to a fixed input, that is 1. So you actually multiply the weights with the input. And then in case of perceptron, you have this step activation function, means it will give you an output which is +1 or -1, right? So what we do is we compute this number. If this number is greater than 0, your output is +1. If this number comes out to be less than 0, your output is -1, right? So this is the, you can say, idea of perceptron that was introduced way back in late 1950s, right? Another, you can say, a rather cleaner version of the previous illustration, you can see here, generalized perceptron with m inputs and m weights, right? And then again, you multiply inputs by weight and you add the bias, and you apply an activation function. Okay, so whenever we are dealing with this, we'll often be using a terminology which we'll call dot product. Okay, so let me explain it once why we call it dot product, so that I don't have to repeat it again and again. So I'll quickly go to the board and tell you why we call it a dot product. So we discussed that within a neuron, in general, we are doing something like this, and so on. Okay, so let's restrict it only to 3 inputs and 3 weights, right? So you see, I can also write this, you can say, expression as something like this. So this is a vector W, right? Normally vector, for vector, either you put this arrow or you make it bold, right? So this is vector W and this is vector X, okay? And normally since we write vector in a column and this we have written in a row, so we call it X transpose, right? If X was a vector, so normally we write a vector like this, and but since we have to multiply, so I have to take a transpose, so normally we write it as X transpose, and this is the vector W. So you see, instead of this, which is actually this thing, a vector representation is X transpose W, right? So you take transpose of X, you multiply it with W, where X and W are vectors of the same dimension. So what is this? This is actually what we call dot product of two vectors, right? In dot product, what you do, you multiply first element with the first element, second with the second, third with the third, and so on, and then you add them together, right? So at some places you will see this notation, somewhere you will see this expanded form, and in most cases you will see this vector representation where this expression is written as a dot product, right? So in the subsequent discussion, whenever I'm using the terminology dot product, I would be referring to this expression, okay? So that, let me shift back to our slides. Okay, so now we have to develop some concepts that how a perceptron will learn, right? But in order to do that, I will now simplify the perceptron. Instead of having, say, m inputs, we'll keep a very simple model of perceptron which has only two inputs, right? So now we have only two inputs, x1 and x2. That's why you see that this summation is going from 1 to 2. And this theta is just another symbol for bias, right? It's the same as b. And as we already discussed that in case of a perceptron, you have a step function that output is +1 if this thing comes out to be greater than 0, and output is -1 if this thing comes out to be less than 0. So now let's see how this will evolve further by fixing some weight values, right? So for example, bias has been fixed to 1, W1 is 3, and X2 is -2. Okay, so I have just taken some random values of weights. Okay, I'm not telling you from where they are coming, but now let's see what actually this y hat would be. So what we will do is it will be 1 plus 3x1 minus 2x2. Okay, so I have done this operation where you multiply and add them together. Then I have to apply some activation function. Okay, so whatever is the activation function is, let me call it G. Okay, and then it will give me this output, which is y hat, right? So in general, this hat is actually used to signal an estimated value, right? Because this is what you are predicting, and for the actual value, we'll be using maybe the symbol y. Okay, so this y hat, by convention, y hat, you can take it as a predicted value. Okay, so now if you focus on this part, what is this? Okay, if you see and if you plot it, this is actually equation of a line. Okay, so let me just plot this line. It would be something like this. So you see, this is the equation of the line, which actually was produced by, you can say, these numbers. Okay, and for the time being, I have just plugged in some random numbers. Now let's see what happens if I take some point in this space. Suppose I take this point, which is -1, 2, and I plug in this equation. Okay, so it would be what? It would be 1 plus 3 times -1 minus 2 times 2. Okay, this is x1, this is x2. So I am simply plugging in these values in this expression. Okay, so it gives me 1 minus 3 minus 2, so it gives me -6. And then I apply activation function on this. So the activation function was something like this, that okay, if the value is negative, your output is -1. If the value is positive, your output is +1. So in our case, the value is negative, so the output would be -1. So it means that for this point, if I plug in here, I get -1 as an output. Now, if you take some other points, for example, if you take a point here or here or here or anywhere, all of these points, you just pick any point, you plug in here, you will get a -1, right? On the other hand, if you take a point on the right side of this line, that is maybe in this region here, you can try any point like 1, 1 or 2, 2 or anything. So in all those cases, it will give you +1. So actually what is happening is that this line is serving like your decision boundary. On the left side, all the points which are on the left side of the line, if you plug any point in this expression, you get a -1. And any point on the right side of the line, that will give you a +1. So actually you have solved a two-class classification problem. This is your decision boundary. On the left side, you have one class. On the right side, you have another class, right? So this is what I'm trying to say, that in all the region above the line, you have -1, and below the line, you have +1. And now you see, if I change these weights, what will happen? Changing these weights can actually change this line, right? For example, for a different value of slope, this line might become something like this, or it might become something like this, or even this, right? So just by changing these values, okay, what will happen? You will be changing the orientation and position of this line. So you will be actually trying to learn the decision boundary that is between the objects of two classes, right? So this is the general idea of how a perceptron will solve a two-class classification problem. Okay, so now just to further emphasize on this, okay, so let's say, okay, we take a very simple example. If you see this, this is, I think, logical OR, right? So this is the truth table of logical OR, okay? So if I plot it, it is something like this. So here I get 0, okay? If both the inputs are 0, I get a 0. For any other combination, the output is 1, okay? So I need to solve this problem using a single neuron, that is using a perceptron, okay? And we just discussed that perceptron can give you a straight line if we are talking about two inputs, okay? If there are more than two inputs, then I'll cover that later. So visually, you see this is one class. All the blue dots, they are one class, and this is your other class. So I just need to draw a line, any line, which is separating the blue dots from the black dot, and that would be my decision boundary. Okay, so I have so many options. So it means if I can draw a straight line which can separate blue points and the black dot, then I can solve this problem with a perceptron. Okay, so let's just take an example of one possible value of weights. Okay, so let's assume W0 is -0.3 and W1 and W2 both are 0.5. Okay, so if you plug in these values, you will get one of these lines. So let's see whether this is solving our problem or not. Okay, so the first input was x1 was 0 and x2 was 0. Okay, this is x1, this is x2, and we say, okay, what is my output? So if you plug in x1 and x2 in this expression, what will happen? It will be -0.3 plus 0.5 into 0 plus 0.5 into 0. So this will become 0, this will become 0, you are left with -0.3. If you apply activation function on this, since it's a negative value, so it will give you -1. So the output is -1. Okay, then I plug in the next combination, which is 0, 1. If I plug in 0, 1, it would be -0.3 plus 0 and plus 0.5 into 1. So it will give me 0.2, which is a positive value, and when I apply an activation function on that, it will give me a +1. So +1 here. Similarly, if you plug in 1, 0, so again what will happen is this is 1, this is 0, it will be 0.5 minus 0.3, 0.2 again, which will give you a +1. Okay, and when you plug in both x1 and x2 equal to 1, means x1 is 1, this is 1, so it will be 1 minus 0.3, which is 0.7, again a positive value, so your output would be +1. So now you see you have -1 this output for this combination, and for all other three you have this, and this is basically the same thing. You can make this -1 as 0 and all this +1 to 1. So it means this is a valid expression which is solving your problem, because you are getting one label for this combination and the same label for all of these three, and this was actually what was desired, right? This is what we wanted. So you see, for the combination 0, 0, we wanted a -1 output, and for all other combinations we wanted a +1 output. So in other words, using this combination of weights, we are able to solve the OR gate using a perceptron. And similarly, without you can say all the calculations, you can also convince yourself that this is one combination of weights for which you can solve the AND gate, right? In case of AND gate, we have 0 here, 0 here, 0 here. So these are zeros and this is 1. So any line which is separating this 1 from these 3 zeros, that will do the job. So this is one possible line. You can plug in all of these values and you can convince yourself that for all of these 3 combinations, you will be getting -1 as an output, because this will give you a negative value. When you will apply the activation function, you will get -1. And when you will give this value, you will get a +1. Okay, so this is what we wanted, that for all of these, AND gate gives you 0, and for this combination the AND gate gives you 1. Okay, so you can actually plug in the values one by one and convince yourself. Okay, so now let's see a different gate, which is the exclusive OR function. Okay, so in case of exclusive OR, you know that if there are 2 zeros or 2 1, the output is -1, or you can call it 0. And if for the combination 0 1 and 1 0, the output is +1, or you can call it 1. So it means that for these two combinations, my output is 1, the blue dots, and the black dots, these are the dots which correspond to, you can say, these two. So now you see, it is not possible for me to draw a straight line which can separate these ones from these zeros. Okay, you see, if I draw, I don't know, if I draw like this, then it won't work. Okay, because 1 is here, 1 is here. If I try draw like this, or I don't know, you try to draw a single line, that is not possible. So you see, if you want to solve this problem, maybe we will need to draw 2 different lines. Okay, something like that. So it means this exclusive OR problem, you cannot solve it with a single perceptron. You will need something else. Okay, because perceptron can only solve something, only solve a problem where classes can be discriminated by a straight line. Okay, by linear decision boundary. That is a problem that you can solve using a perceptron. Okay, another concrete example, not from the gates, but maybe you can correlate it more with the real world. Okay, so we take an example that suppose you have a course, you have a 1 week course on deep learning, right? And we want to predict whether a candidate will clear this course or not, right? And we actually use 2 features, that how many lectures in a week the candidate will attend, and how many hours the candidate will dedicate to the assignments. Okay, and suppose we have some data from the previous batch, right? Maybe the course was offered in summer, 1 week course, and we have data from the previous batch. Okay, so these, you see, on this axis we have the number of lectures attended. So it means, maybe say this is 7 lectures, say this is 6 lectures, and so on. And on this axis we have the number of hours you dedicate to assignments. Okay, so all the green dots, these are the candidates who could clear this course. And these 3 red dots, these are the candidates who could not clear. Okay, so you can already guess that, you see all the data which is lying in this region. So what is actually happening, that they have very few lectures which they have attended, and they have dedicated very fewer hours to the assignment, right? So it makes sense. Okay, now, so from this training data, what we want to do is that if there is a perceptron, then it should learn a boundary like this. Maybe I'm just guessing. Okay, and then suppose you want to predict that, okay, will I pass this course if I study for 4 lectures and I spend 5 hours on assignment? So it means this is you. Okay, and you want to predict. So maybe if your network is trained, this is the decision boundary. So your decision would be that you are likely to pass this course, right? Because you are lying on this part of the decision boundary where we expect the candidate to clear the course. Okay, but how it will actually learn, how you come up with this line? Okay, so now we are discussing it from that perspective. Okay, so suppose initially we have this perceptron, okay, which is accepting 2 inputs, but here we this is not trained, so here we have some random values. Okay, we don't know what is here, we just initialize with some random values. So actually we know that with this input you should pass the course. Okay, y is 1, it means you should pass the course. Y equals -1 means you will not pass the course. Okay, so now if I plug in this 4 to x1, okay, and this 5 to x2, I multiply them with random weights, I apply an activation function, and suppose this gives me the output, instead of 1, it gives me the output which is 0. Okay, which is not correct. this was the correct output that I should have, but the system is giving me this output. Why? Because our network is not trained yet. We have some random weights here, so they can give you anything. They can give you the correct value, they can give you the incorrect value, right? So now we have to train the network. Okay. Previously, I told you that cashier example where we were simply guessing the weights, right? But naturally, when we are training a network, guessing will not work. We need to have a more formal way of how the weights can be learned. Okay. So what we do is, in order to train a neural network, we define something which is called a loss function. Now, what is a loss function? Loss function is actually a formal way of saying how much error your network is making in predicting the classes. For example, in the previous example, your bill was 850 and you predicted 500. So the error that is between 850 and 500, that is your loss. Okay. And if you write it formally, okay, so maybe for loss function, you will normally see this symbol, and you have a predicted value which the system has given you, and you have the actual value. Okay. So this you can see here that there's a loss function. To this function you give your predicted value and your actual value, and it tells you how much is your loss. Okay. This can be simply, you can subtract them and take the absolute value, you can subtract them, take square, so it can be anything, right? But the idea is that it will tell you how good your prediction is, or how much error you are making when you are making the prediction. Okay. Now this y will come from data, because you already know the label of the data, and this y hat you are computing actually from the network. So just to recall that this y hat is computed like this: you have two inputs, two weights, you multiply them, you add by, so you apply activation function. This is your y hat. Okay, so y hat is computed from the network, and these are actually for the time being some random values. Okay, and this y is coming from data, because we are dealing with supervised learning, so your data would be labeled. Every example will have some label. Okay, now we have some discussion for which I will need your attention a bit more than usual. Okay, so you see in the previous example, I only have one sample which I fed to the network and I computed loss. But whenever you are training the network, okay, this is my one, you can say, training example. This was my first sample. So maybe I will have many training examples, not just once. And for each training example, I will have a label. Okay, 1, 1, 0, 0, 1, pass fail, and so on. Okay. So when you are computing the loss, you need to compute the loss over all the training examples, right? So if I have m training example, I compute the loss for the first training example, then second, then third. So this I that you see here, it is going from 1 to m. So it means you first compute the loss for the first training example, second, third, and finally for the last training example. You add them together, and for normalization, you simply divide it by the number of examples. So this is basically your key expression that we will be using in the subsequent discussion. And normally we use the symbol J, right? So this J is actually, you will see different terminologies for this, cost function, objective function, risk, or something like that. Okay. So normally some people would be using loss and cost interchangeably, right? But for some people, loss is something that you compute from single training example. Okay, and cost function is something in which all of your training examples are incorporated, right? But it's just a matter of terminology. Even if you use them interchangeably, that's okay for me. Okay, now as I told you, just an example of a loss function, that how can you compute loss. For example, one common example of a loss function is that you simply subtract the values and take the square. Why do we take the square? To avoid negative values, right? So for example, if my bill was 850 and someone is predicting 500, so you simply take the difference square. And similarly, there will be many training examples, so you compute this for all the training example, you add them together, and then you normalize it. Okay, and one last thing before I take a pause, you see I have written W here. So why is it W? So it simply means when I'm writing J of W, it means J is a function of W. J is dependent on W. And why is it dependent on W? Because if you see on the right side, this Y hat, this y hat is actually dependent on W. Why? Because how you are computing it, you are computing it like this, something like this. Okay, you can write x transpose W or W transpose x, it is the same thing. So since this y is being computed using weights which you have to learn. That's why we are saying that this j is a function of w. If I change my weights, this whole thing will change, right? Because you cannot change y. Y is a fixed label which you get. The only thing that you will change is this thing which you are predicting. And how this will change? If I change the weights here. If I have 2 3 here, I predict something else. If I have 20 and 30 here, I predict something else, right? So that's why we are saying that this cost function is dependent on weights, but you don't see any weights explicitly on the right side of the equation. The reason is that weights are in this expression yi. When you are predicting the value, you are predicting using a perceptron, and you are using the weights to predict that value, right? So that is why we say it's a function of wj, or cost function is a dependent on your weights. Okay, so I think we had sufficient discussion. So if there is any point you would like to make, please let me know. Okay, so now once we have the expression for the cost function, now we need to find the values of weights, or we need to learn the values of weights. And what is the criteria for that? Okay, again, please see this carefully. So you see, this is our loss function, which is coming from the previous slide. Okay, this one. And we are taking sum over all the training example. Now you see, what is our objective? Our objective is that I have to find those values of weights for which the error is minimum, right? When you say cost, this is actually an error, and error should be as low as possible, right? And how the error would be low? Error would be low once your predicted value is very close to the actual value, right? For example, if the output is +1 and we are predicting +1, the error is 0, right? Because whatever was the true value, you are predicting exactly the same thing. So now, but the problem is that when I'm feeding my data to this perceptron, okay, these weights here, they are actually random. So when I give my input, multiply them with some random values, my error could be anything. Okay, so the idea is that I have to find those values of weights for which my error is as low as possible. Okay, means find the values of weights for which this expression, which I have highlighted here in the red blocks, this is my error, this should be as low as possible. So whatever I have said, find values of weights for which error is as low as possible, or the error is minimum. If you write it mathematically, you call it argument, right? So it means you have to find those values of w for which this thing in the red box, it has the minimum value, right? So a little while back, in response to a query, I was telling that, for example, suppose if this is my error, okay, and I have only one weight, this is w, or let's call it w1. So you see, if I pick this value of w1, my error is here. If I pick this value of w1, error is here. But if I pick this value of w1, okay, say this value is 2, I have the lowest error. Okay, so this is the whole idea, that when I write this, it simply means find the value of w for which this expression within the red box, which is actually error, it is as low as possible, and it makes sense, right? So it is just a mathematical way of writing this thing. And instead of always writing this expression, I told you that we represented it with the symbol j, which is our cost function. So in simple words, we are saying you have to minimize the cost. You have to find the optimal value of weights so that this j is as low as possible, right? So in other words, whatever I have said, it is also written here. W is a set of weights. This is not a single weight, right? If you have like 2 inputs, you will have 2 weights and 1 bias. If you have 3 inputs, you will have 3 weights, right? So that's why we are writing W. It is not a single weight. It is the set of all the weights that you have in your network, right? So we are saying we have to find those values of weights for which the loss function JW, it has the lowest possible value, right? And as I was telling you, a very famous method to do that I'm sure you must have seen in machine learning, that is called gradient descent. Okay, So I will not be deriving complete gradient descent, but I'll just be giving you an overview so that you can recall from your previous knowledge, right? I'll show you the expression, but if you are interested in derivation, I can share, but I'll not cover it during the lecture, right? So the general idea of gradient descent is that suppose we have only two weights, okay, W1 and W0 or W2, whatever you want to call it, okay. And on this axis we have the error, right? On the Z axis we have this J, which is actually our error. So you see, for different combinations of W1 and W2, you will have different values of error. Okay, for example, if I have W1 is 0 and W2 is 0, what is my error? My error is here. If W1 is -2 and this is 2, so I am somewhere here, maybe error is here. Okay, so by looking at this error surface, you can easily guess that what do we want? We want that combination of W1 and W2 for which this error is as low as possible. Okay, so maybe it is somewhere, I just guess here. Okay, this is the point, let's assume this is the point where error has the minimum value. So it means that my network should learn this value for W1 and maybe this value for W2. So this is the general idea, okay? But of course, it is not possible that I plug in all possible combinations of W1 and W2 and then I compute error at every possible combination and then I say, okay, I'll pick this, okay? And in this case, you only have two weights, W1 and W2. When you are solving a practical problem, you will have hundreds or maybe thousands or even millions of weights. So it is not possible that you numerically try different combinations and guess, okay, this would be the combination which is giving me the minimum error. So on the other hand, we do smartly. What we do is we do what is called gradient descent, right? So you must have seen that very famous example that whenever you are trying to understand how gradient descent works, you assume that you are in a park which is very hilly. You have small hills, you have valleys, and so on, right? So what we do is again you have two weights, W0 and W1, and on this axis you have error, which is dependent on these two variables. So you pick some random value for W0 and W1. Okay, suppose I pick W0 this value and for W1 I pick this value. So basically I am on this point. Now assume that this is not an error surface. It's basically map of a park, and the park is not flat. You have hills, you have depressions, and so on, right? So whatever location you have randomly picked, so you can assume that actually you are standing on that location. Okay, so you are standing there on this point, and then what you have to do, you have to look all around you, okay, and you have to see, okay, your objective is to go down from this hill, okay, or to go to a point which is as close as possible to the ground. So what you will do is you will see 360 degrees around you and you will say, okay, which is the direction which is most steepest. Steep means, for example, this is more steep, this is less steep, this is less steep, okay. So this is very steep, so if you slide on this you will quickly go to the to the ground or towards the earth, okay. So you have to pick that direction which is most, you can say, steep, okay. And then what you will do is you will take a step in that direction and then you will arrive here, okay. And then again you will look around you and you say, okay, which is the direction which will quickly take me to the ground. So you say, okay, this is very steep, I take this direction, okay, and then you arrive here. So you will keep on doing this, okay, and eventually we expect that after some iteration you will arrive at a point, right, which at which the error is low, and corresponding to this point now you will pick the values of W1 and W2. So you say, okay, here my error is very low, so I pick W0 as 0.4 and W1 at 0.8, okay. So this is basically the this is just for understanding purposes how actually this is done. So if you remember derivative gives you basically slope, okay. So that's why when we say you have to look for the steepest direction, so what you will do, you will actually compute the derivative of this surface, okay. And just to give you an idea why this will work, okay, first let me just show you the same thing which we discussed, and then I tell you how actually this works. So this is the whole idea, and I told you that in order to find this direction, which will quickly take you to the ground, you have to compute this expression. You have to compute the derivative of this surface. What is this surface? J. You have to compute the derivative of J with respect to your weights. Okay, now this W is actually means you have to compute this, and you also have to compute this. So in this example, I have only two weights, so that's why I have only two derivatives. If I have say 10 weights, so I will have 10 terms like this. Okay, so now let me show you the algorithm for gradient descent. Again, I'm not going into low level details because this is not the content of this course, but just for completeness, I'm just repeating it, right? So if you see it from the perspective of how do we learn, so the algorithm says that first you initialize weights randomly. Okay, so if you have two weights, say W0, W1, you simply give them some random values. Okay, any random values, positive, negative, whatever you like, right? And then you have a loop. And what you do in the loop, so these are the basically steps where you are finding the direction in which you have to move, and then you are moving. Okay, so I told you you have to find the direction which will quickly take you to ground, and then you have to take a small step. So this is actually finding the direction, and this is actually taking that step. Okay, so here you are finding which direction you should go. Okay, so this will keep on, you can say, iterating until your algorithm will converge. There will not be much of change in the weights, and you will stop there, right? So in this, the key expression is this one. Okay, and what is this expression? This is your previous value of weight. This is the derivative you have computed, and this is a parameter which I'm sure you are familiar. This is called learning rate. Now, what is actually learning rate? Learning rate controls how quickly you are going down, right? For example, when you are standing on, say, this hill, okay? So if you are taking very small steps, so it means you have a very small value for learning rate. On the other hand, if you are standing on a hill and you are taking very big steps, so it means this learning rate has a high value. So when you are descending from a peak, learning rate actually controls what is your step size, how long a step you take as you go towards the ground. Okay, and I'll just quickly explain this expression a little bit, maybe on the board, and then I'll show you without derivation, I'll show you the final result. Okay. So let me just go to the board and explain to you that why does it work. Okay, so the best, you can say, way to understand is by assuming that we have only one weight W1. Okay, and here we have error or J. Take a J or maybe error, whatever you want to call it. Okay, so suppose this is my error surface, right? We start, our objective is this point. Why? Because this is the point where error has the minimum value. Okay, so what I do is I say, okay, since I'm starting randomly, so let's randomly start here. Okay, suppose here W1 is maybe, what do I call it? Say 4. Okay. Now you see what I'm saying. I'm saying that you have to use this expression to update the weight. Okay. Your initial value of W1 is 4. Okay. Now what is this? You are saying compute derivative of J with respect to W1. So from last time we discussed, even if you don't need to remember any formula, derivative is actually the slope at this point. See, if you remember, it was slope. I told you that derivative is just a fancy name for slope. So what is the slope here? Okay, so I think it seems like it's an angle of like around, just guess, 45 degrees. So maybe the slope is 1. Okay, and let's fix this learning rate equal to okay, let's fix it to 1. Although 1 is a very big value, but since we are just discussing, so let's fix it to 1. So this would be 4 minus 1 into, what is the derivative here? Say derivative is also 1. So what will happen now? It will become 4 minus 1, which is 3. So the new value of W1 is actually here, which is 3. So you see, you are moving towards your target. Now you will repeat it again. You will say, okay, what is slope here? So I think slope here is like 0.5. So now your expression would be W1 would be 3 minus 1 into 0.5. So it will give you 2.5. So the new value of weight would be 2.5. So you see, slowly you are going towards your target. On the other hand, suppose you started here. You started with W1 as -4. Okay. So now what will happen? Let me just erase the bottom part so that you don't confuse it with the previous text. Okay. So we start with a negative value of weight and we say this is the expression we use to update the value of weights. Okay. So the new value of W1 is -4 minus learning rate is 1. Now you see this line is like this. So it has a negative slope. So maybe the slope is like -1, -1.5, whatever you want to call it. Okay. I call it say -1. Will be -4 plus 1 and it would be -3. So -3 would be some point here. So again you see if I choose a point here, this expression is taking me towards my target. My target is actually this point. Okay, so for both the we took an example where slope was positive and we took an example where slope was negative. So you see in both cases it is taking us towards our target. Now it's a good idea that at the same time, let me tell you what will happen if my learning rate is too small. Suppose my learning rate is 0.1. Okay, when I was saying this, it is the size of the step you are taking. So you see, if this value was 0.1, what will happen? This will be 0.1. So instead of -3, it will become -4 plus 0.1. So maybe it will become -3.9. So from here to here, rather than from going from -4 to -3, now you will be going from -4 to -3.9. It means you are taking a very small step. You are moving towards your target, but the step you are taking is very small. On the other hand, if it's a very big value, suppose it is say 2. So what will happen? This would be 2 into -1. So from -4, you will take a big jump to -2. Okay. So you see, what actually happens is that sometimes it's hard, right? Because if you are taking very small steps, it will take a long time to converge. But if you are taking very big steps, the risk is that suppose I am here, so my learning rate is so big that instead of stopping here, maybe I can overshoot it. Okay, from here I jump here, and then from here I again jump here. So it will keep on oscillating, and it will not be actually stopping at this point which I actually need. So in many cases, if you are talking about the classical version of gradient descent, the learning rate is fixed, right? But there are many variations of gradient descent in which what happens is that initially, since you are very far from your target, so the learning rate has some high value. Okay, but as you progress, learning rate keeps on changing, right? So as you come closer to the target, the learning rate keeps getting smaller and smaller, right? Means it is an adaptive value, it is not a fixed value. But there are different variations of gradient descent. So what we are talking here is actually the classical version of gradient descent. Okay, so let me now go back to the slides and then I show you the same thing. Okay, so here we were saying this was our key expression. Okay, and now this expression would make sense to you after all that discussion. But the only thing is that this W, if I have 10 weights, so I have to repeat it for 10 weights. Okay, means this W is not a scalar, it is not a single value. This W is referring to all the weights. So the example I gave you, I had only W1, but if you have say W2, W3 and so on, so you have to repeat this process for every value of W, 1, 2, 3 up to M, and depends how many weights you have. Okay. Okay, so now the thing is that when we were discussing, I visually illustrated that what is this thing. Okay, this is a derivative, so it was very easy for me that okay, this is the point, so you actually compute the slope. But once you are doing it numerically or mathematically, you need to actually, this J will have some expression, right? You will have a loss function. If you remember, this was, we said something like predicted value and actual value. You are doing this, you are taking summation, right? So this was actually this. So it means when you are solving it, you are actually taking derivative of this. Okay, and then you are solving. So if you want its derivation, right, it's in the ML course. I might have some slides for that, but I'll not be deriving it. But if you solve it, eventually, if you take the derivative of this expression, that is mean square error loss function with respect to W, you end up with this thing. Okay, now this is, what is this? This Y is your actual value. And just to make it simple, I'm calling it target. Okay, so that you don't confuse. This Y hat is your predicted value or the predicted output, which we are representing by a symbol O. Okay, so if I write it just so that you see it stepwise, why I have written Wi? Because this I can be 1, 2, 3, depends how many weights you have. Okay, so you have to repeat this process for every value of I, depending on how many weights you have. This is actually target, which was your Y, minus predicted value, which was Y hat, multiplied by input xi. Now what is xi? If I is 1 here, W1, this is x1. If you are talking about W2, this would be x2, right? So this is basically how how you will actually plug in this into this expression. Okay, for example, if I have to update the weight of W1, my expression would be W1, right? Since it's minus and minus minus will become plus, I'm simply plugging in this expression. Learning rate, target minus output, and x1. Okay, because I'm talking I is 1, I am updating W1, so here I have x1. When I will write the same thing for W2, you simply convert this to, this will become 2, this will become 2, and this will become 2. Okay, so this is basically what the weight update equation is, right? That previously when we started our discussion, I asked you that you can assume any random value of weight, but actually the weights will be learned, and this is the algorithm which we saw on the previous slide, this one, that you have to repeat, and it will allow you to learn the weights. And this is, you can say, more in-depth detail of how actually the weights will be updated. I'll also do a numerical example of using this, you can say, weight update equation, so that it becomes more clear to you. But before that, I just need to cover 3 slides, okay, and then we'll take a pause and I'll do a numerical example. You see, when we are talking about this, initially in the loss function, we have sigma, right? Because we were adding the error of multiple training example. But you see here, there is no sigma. Why? Because once we have done this derivation, we have done it for a single training example, right? And once we have derived, we have to put the sigma back. So depending upon how you deal with multiple training examples, there are different, you can say, strategies that you can use with gradient descent. One strategy is called batch gradient descent. Okay, now what happens is that, you see, in the previous slide, we had written this expression only for one training example, but we don't have one training example, we have M training example. So what I will do is, I will feed the first training example, I will compute this. Okay, for training example 1, I compute this error, say E1. Then for training example 2, I compute this, and so on. I keep on doing it. I have all these M values, and then I will add them together, and then I will update the weight. Okay, if this I is confusing you, I is, you can assume this is 1. Okay, because we are talking about W1. When we are talking about W2, you simply replace 2 here. So you see what is happening now. When I'm calculating this term, I have to find error on the complete training data. Suppose I have 1000 examples, so I have to find 1000 values of this, add them together, and then I will update my weights. So you see, in other words, your algorithm has to see the complete training set for one iteration of gradient descent, because once you have computed this, only then you will update your weight, that the new value of W1 is, say, 0.2 plus learning rate into this thing. To compute this, you need to see all the training examples, right? Which can be very, very slow, especially if your training data is in thousands or maybe in millions. Then it means that the batch gradient descent is not a good option, right? Because you have to see all the training examples just for one iteration of gradient descent. Okay, now we see the other extreme, which is called incremental or stochastic gradient descent. Now what happens in this? Instead of a summation, you see we have converted it into a loop. Now what is happening is M is again the total number of training example. When J is 1, it means we are talking about the first training example. Okay. So you feed the first training example to the network. You know the target, you have the predicted value, you compute the error, and you update the weight. Then you feed the second training example, you again update the weight, and so on. Okay. So now what we are doing is that we are updating weights by looking at one single training example. It means I see one training example, the weights are updated. Okay, so let me just draw it. These are my say 4 training example. So I see the first training example, I compute, I already have the target, I compute the predicted value, I will update the weight. Then the second training example, third training example, fourth training example. Okay, and when my data set is exhausted, I go back again to the first training example. So this is now another extreme. Previously we were looking at the whole data set just for one iteration of gradient descent, and now we are updating weights just by looking at one single training example. So you can guess already that maybe it will be very noisy, right? Because one single training example cannot be very reliable to update the weights. So a solution in between that we normally use is called mini batch gradient descent, right? Here you are actually using the complete data set, which is very slow. Here you are looking at only one training example. So a solution in between is mini batch gradient descent. Now what you do is, let's suppose this is your whole data set, say, okay, suppose there are 1000 examples. You divide this data into mini batches and you say, okay, my batch size is say 100. So it means if I divide it into batches of 100, I will have 10. These are 100, these are 100, these are 100. Okay, so I'll have 1 2. So I will have my data divided into 10 different parts, or these are called 10 different batches, right? So in one batch I have 100 examples, then 100 in the second batch, third batch. So total I will have 10 you can say subsets. So in mini batch graded descent, what we do is we feed these 100 examples, we will update weight. Then we'll feed these 100, we'll again update weights. And then this and this and this. When the entire data set has been fed to the algorithm once, it is called one epoch of the training. Since data set is finished, I will again go back to the first set or the first subset or the first batch, and I'll keep on repeating this process. Okay, so basically this is something that you will see when you are actually executing. So it means now when the complete data set has been fed, we are calling it epoch, right? So in one epoch, in this case, I have actually 10 steps. Why 10 steps? Because there are 10 batches. Okay, so it means when you will run this algorithm, it will feed batch 1, batch 2, batch 3, batch 10. When everything is fed, so it will say, okay, one epoch is done. And then again, it will start with batch 1, batch 2, and it will say, okay, second epoch is done. And so on. You will have defined, okay, maximum number of epochs is 50. So your algorithm will run for 50 epochs, and then it will stop, or it will maybe converge even before that, right? So this is the, you can say, theoretical idea of how you can use learning with a perceptron, right? So whatever I have shown you, I will show you a numerical example where we'll try and learn the weights for a perceptron using a simple example. But before that, if there's something you would like to ask, you are welcome. Okay, so now is the time to put all the components we have seen to a practical example, rather a numerical example, where you will actually see how an algorithm learns, how a perceptron learns. Okay, so you already know all the equations, but I'll plug in some numbers and you can actually see that the weights are changing and how we initialize with some random weights, and eventually the perceptron is able to learn the correct weights, which give it a correct classification on your data, right? So the example we have taken here is definitely we are dealing with a single neuron with two inputs, perceptron. So we need to take an example which can be solved using a perceptron. It means where you can find a linear decision boundary. Okay, so the example you see is this is an AND gate. Okay, you have two inputs, x1 and x2. Okay, so let me just take the cursor here. Okay, so this is your input x1 and this is your second input, which is x2. Okay, and we already know the target that, okay, when x1 is 0, x2 is 0, output should be 0. Similarly for this combination 0, 0, and when both the inputs are 1, the output should be 1. Now, to make things a bit simple, okay, we have fixed some things. For example, we have already fixed that the learning rate, eta or alpha, whatever you call it, that is 0.1, which you see at the bottom of your screen. And this threshold is actually bias, right? As I told you, for bias, we'll be using different notation, sometimes W0, sometimes B, sometimes theta. So this is actually 0.2. So although practically once you are implementing, bias is also learned. Okay, we cannot fix bias. But for this example, to keep things simple, I have fixed this value to minus 0.2 so that we don't have to change it on every iteration, right? So actually, once you are doing things, this is something which will not be fixed. This will also be learned. Okay. So for two inputs, you see, if I draw a perceptron, so you know W1x1 plus W2x2, and this is fixed. This is 0.2. Okay. So this is our expression. We don't know what is W1, W2. We want to learn them using the algorithm we have just seen. Okay. So we initialize W1 and W2 with two random values, 0.3 and minus 0.1. Okay. And just for the sake of this example, I have taken a positive value and a negative value, right? Because weight can have a negative value as well. So now what we do is we have to plug in these weights, okay, and compute what is the output, what is the predicted output. If you remember what we do, we compute the prediction, we compare it with the target, and then we update the weight. This is the process we'll be following, okay? And in this example, we are using stochastic gradient descent. It means we will feed one training example and we will update the weights. Why? Because our data is very small. I only have 4 examples because with 2 inputs, binary inputs, only 4 combinations are possible, right? So that's why I am feeding one example and I am updating the weight. So this is a stochastic gradient descent. Okay. So now let's plug in these values of weights which we have randomly chosen. So this will become 0.3 x1 plus sorry, say minus 0.1 x2 minus 0.2. Okay, so this is my expression if I plug in the values of weight. Now what I do, I feed it the first training example, which is this. X1 is 0, x2 is 0. So when I feed 0.3 into 0, this will become 0. When I feed this, this will also become 0. And this will become minus 0.2. Okay, so it means I get minus 0.2. Now I have to apply activation function G. So the activation function tells me that if it's a negative value, your output is minus 1. If it's a positive value, your output is plus 1. Since it's a negative value, my output is minus 1. Okay, but in this case, since we have here 0 and 1 rather than minus 1 and plus 1, so whenever I am getting minus 1, I will treat it equivalent to 0, and whenever I'll get plus 1, I'll treat it equivalent to 1. Okay, this is just a matter of label, right? Because in the truth table, I have not written minus 1 and plus 1, I have written 1 and 0. So when it is minus 1, I'll treat it as 0. When it is plus 1, I will treat it as, I will treat it as 1. Okay, and this is 0. Okay, so it means now what is the output I am getting? Minus 1. So the actual output my network is giving me is 0. Okay. Now, if you remember, what is the weight update equation? The weight update equation was W1 is W1 plus learning rate target minus output into X1. Okay, this is the expression I showed you a little while back. The only difference is that instead of eta, I'm using the symbol alpha. Okay, so it means this would be W1 was 0.3 plus alpha is 0.1. Okay, target is 0 and our output is also 0. Okay, so it means the error is 0. When I do target minus 0, whatever was the target, I'm getting the same thing. Okay, and this is x1, this is also 0. So when I do this, this whole terms actually becomes 0, and I'm only left with 0.3. So the new value of W1 is 0.3. It means there is no change in W1. Why? Because this term becomes 0 accidentally or for whatever reason, right? So it is possible that weights are not changed. Now let me do the same thing for W2. So for W2, again, the expression would be W2 plus learning rate, target minus output, and be careful, now we have X2 here. Okay, if you remember, this was I. So when I'm solving for weight 1, I have X1. When I'm solving for weight 2, I have X2 here. Okay, so let's try this. This would be minus 0.1 plus alpha is 0.1. Okay, what is target? Target was 0 and output is 0. So this will again be 0 minus 0. So this term will again become 0, and that value of W2 will also not change. So the new value of W2 is same as old value, which is okay. It is very much possible that you don't have a change in the weights in every step, right? Okay, so let me just show you the cleaner version of this. This is a clean version of the computation which I just did. Okay, and the key expression is this one. Okay, this is the key expression. Since I have two weights, so for I, first you will plug in 1, and for I, you will plug in 2. If I had 10 weights, I have to repeat this 10 times. Okay, and if I'm updating W1, as I told you, here I have X1. When I am updating W2, here I have X2, right? You can just correlate this, both of these, with this general expression. So this is target minus output. So in other words, if my output is same as target, so actually this term would be 0 and there would be no update in the weight. So you see, it is making sense. Why is it making sense? Because with current weights, we are getting the target output. So it means there is no need to change the weights. That's why the weights did not change here. Okay. Now let's feed it the second training example. So for the second training example, now I will use these values of weights. Okay. By chance they have not changed, but if they had changed, then of course I would have used those new values. But since they have not changed, so I simply copy these values here. Okay. And I'm not doing it, but if you will do it again, there will be no change in the weights. Okay. You can actually do it again. What will happen is that whatever is the target, your network is also predicting the same thing. So there will be no change in the weight. Okay. But for the third example, there will be some change. Okay, so now let me do it for the third example. So for the third example, okay, you see again, whatever weights you have here, you copy them, okay, and now you feed it with the third training example. Okay, so now when I feed it with the third training example, let me just do it. Okay, so this is our expression. Okay, so W1 is 0.3. Okay, X1 is 1 plus W2 is minus 0.1 and X2 is 0. Okay, and then you have minus 0.2. So now once you do it, it will become 0.3 minus 0.2, which is like 0.1. Okay, and 0.1 is greater than 0, so I will get a value which is plus 1. So when it is plus 1, it means my actual output is plus 1. So now you see, target was 0, but I am getting 1. So it means now there would be something that will change. Okay, so let me just quickly do this, and then I take your query. Maybe it's better if I do it on the board, because otherwise it would be very messy. So let me just come to the board. Okay, so here what we are saying, W1 is W1 plus learning rate, target minus output into X1. Okay, and let me remind you, W1 was 0.3 plus this was learning rate, which is 0.1. Okay, this time the target was 0, but I am getting a 1. Okay, so this was 0, but network is giving me 1, which is the output, and X1 is actually 1. So if you do this, it will become 0.3 minus 0.1, which is 0.2. So now you see the value of W1 has now changed. From 0.3, it has now become 0.2. Why? Because this time in the previous cases, this term used to be 0, but now this is not 0. Target was 0, but the output of the perceptron is 1, so I have some error. Okay, now let's go back to the slide, and let me show you from there. Okay, so you see this time we have a change in the weights. W1 has changed, but W2 still has the previous value. Okay, Now I'll feed the last training example. You can repeat this process and again you will have some values. So you see, when I have fed it with the fourth training example, now this was my complete training data. Now the training data is finished, so one epoch is finished. Now I am starting the second epoch where I will repeat this process again with the first training example, second training example, third and fourth. Okay, so you will keep on doing it. Okay, and maybe if you see at the bottom uh, of the table where we have epoch 5. So after 5 epochs, what has happened? Every example has been correctly classified. Means whatever is the target, we are getting the same output for every single training example. You see, this was our target, and this is the actual output we are getting. So you see, as you were asking, now I do not need to continue learning. Now I had 4 training examples. All of my training examples are correctly classified. So it means the correct weights are 0.1, 0.1. I can stop here. Even if I keep on running it, nothing will change, right? Because every time I will get error which is 0, and when the error is 0, weights will not be changing. So you can say in 5 epochs, this algorithm has converged. And one last thing before we discuss this, you see, when we are changing weights, if you remember when we started our discussion on Perceptron, I told you that, say, suppose this is your equation, eventually your weights are 0.1, 0.1, and bias is like 0.2. So if you plot it, this is actually a line. So you see, once your algorithm is learning, these weights are changing continuously. Okay, maybe we started with 0.3 and 0.1, then 0.2 minus 0.1, then the weights become this, and then this. So actually what is happening is that you see this line is changing its orientation. Initially it was like this, then it became horizontal, then it moved upwards, okay, and then eventually it actually acquired a position where all the positive examples were on one side of the line and all the negative examples were on the other side of the line. Okay, so this is actually the numerical way of looking at it, but you should also be convinced that if you plot all of these lines using some tool, so lines would be continuously moving, changing its slope, changing its position, and eventually once your algorithm has converged, the line would be in a position where one class is on the left side of the line and the other class is on the right side of the line. And this is where we started our discussion with. Okay, if you remember that pass fail example. So I just had drawn a random line, but now things are not random. Now you actually know how that line is being generated, how you are learning the correct combination of weights that will actually end up in a line which will allow you to separate the two classes. Okay, so that I'll let you ask any queries if you might have. Okay, so let's go further. We have just seen perceptron, right? And perceptron is a single neuron which gives you only two outputs, +1, -1, or you can say 1 or 0, right? It means it can only give you two outputs. Okay, so now let's apply a perceptron to solving something else rather than just an OR gate or AND gate, right? So take an example that suppose we want to predict whether someone is going to buy a car or not, right? And what are the parameters that we take into account? We say what is the salary of the person and what is the family size. Okay, so these are the two parameters, salary and family size. Okay, so here we say, okay, maybe we have some training data, 5 examples that if the salary was this and the family size was, sorry, 8, then that person actually bought a car. Okay, and similarly you have some examples where the person did not buy a car. Okay, so these are few examples, but of course you will have many. And maybe if I plot it, so it is something like that. Okay, so the green dot actually tells you that the person is going to buy a car, and the red dots are actually those individuals who did not buy a car. Now suppose we execute the same perceptron learning algorithm which you just saw in the previous discussion, right? But now the thing is that in the previous example, your problem was fairly simple, so you could find a decision boundary which correctly classified all of your training data, right? But in this case, of course, since both the classes are overlapping, so the algorithm will find some decision boundary which again would be linear, but it will not correctly classify 100% of your data, but that's okay. Okay, we don't care about it. Okay, So maybe this is the decision boundary which you see here. And again, it's a straight line because we are talking about a perceptron. So anything which is in the red region, you will say they will not buy a car. Okay, they will not buy a car. You output 0. And anything which is in the green region, your system is predicting 1, that anything here they will be buying the car. Okay, it's okay, fine, but there's a slight problem with that. You see that your perceptron has a very hard, you can say, decision, either 0 or 1. You buy or you don't buy. It does not give you a probability or something in between. Means either it gives you a 0 or a 1. There's nothing in between. And why this could be a risky thing, because let's see these two dots which are highlighted here. Okay, so you see this person has a very big family and he has a very low salary. So this is very far from the decision boundary, means there is no chance that he's going to buy a car in near future. Okay, on the other hand, this person has a large family size, but he has some handsome salary and it is very close to the decision boundary. So the probability that this person would buy a car is relatively high as compared to this person. Okay, maybe he gets a jump in the salary, so he will come in this region, right? Means you see he's very close to the boundary, so maybe he gets an extra increment, so he will be in a position to buy a car. But your perceptron is giving the same output for this person as well as for this person. Means he is treating both of them as as the same category, that they won't buy a car because it is only giving you the answer in yes or no. So on the other hand, rather than yes or no, if we output a probability, then maybe for this person the probability is like 0.1, but for this one the probability could be like 0.4, 0.45, means it is relatively high, right? So that's why practically instead of using perceptron today, we use something which we call sigmoid neuron. Now what is sigmoid neuron? Nothing, exactly the same thing. The only difference is that instead of step function which gives you output +1 and -1, we change the activation function to sigmoid. And we discussed in detail last time that a sigmoid function gives you output between 0 and 1, not just 0 and 1. Okay, perceptron was giving you only 0 or 1. Now this can give you any value between 0 and 1, and that can be considered as a probability of buying the car in this example. Okay, so this is what I'm trying to say, that you see instead of just 0 or 1 decision, if you change the activation function to perceptron, now you see these different colors, they are actually just for illustration purposes, they are telling you different probabilities, right? For example, you see this dark green, so means this person has a probability close to 1 that he is sure to buy a car. This one is maybe very close to 0, so his probability of buying a car is close to 0. But you see, if you see this person, now maybe he has a probability which is like 0.3 or 0.4, right? Similarly, this person and this person, they are not having the same, you can say, value which was 1 in the previous example. This one has a higher probability as compared to this one because he has a very small family and his salary is quite good. Okay, so now what we have done is that we have simply changed our activation function G, which was previously a step function, which was giving us only two outputs, 0 and 1 or +1, -1. Now we have changed it to a sigmoid activation function, which we discussed previously. Okay, so now there's something important before I give a formal name to this one. Whatever we have done, it is something that you call logistic regression, but I'll come back to this slide later. Just one important thing, that you see, the classically when we say perceptron, we are talking about this. Okay, but today even if you are using sigmoid, people would be using the term perceptron. Okay, so technically maybe this is not correct, but historically, even if the activation function is something else other than step function, today in the literature, in the books, in the paper, people will be calling it perceptron for historical reason. Okay, no one will be calling it sigmoid neuron, right? So this is just something that you should know, that historically when we say perceptron, so perceptron means a step function. But later on, the step function was replaced by a sigmoid, but the term perceptron continued to exist. So if today you are saying that I'm using a perceptron, it is understood that it is most likely you can be using sigmoid activation function. There is no problem with that. Okay, so now let's give a formal name to this example. Okay, and what I'm going to tell you is nothing new, the same example, but just with some fancy terminology, and we are calling it logistic regression, right? But before I tell you logistic regression, I need some feedback from you that okay, first I want you to tell me from your knowledge of machine learning that you must have seen some problems of classification and some problems of regression. Okay, so I would like few of you, if you can explain the difference between the two, that what is classification, what is regression. This is a typical question that someone would ask you once you appear for an interview in a job that is related to machine learning. There's 90% probability that the first question they would ask you is this: what is the difference between classification and regression? So can anyone recall or tell me? And no one is willing to tell. You can talk, or you can type, right? uh, okay, let me see. I have a couple of answers. Okay, we have one suggestion that classification is about label and regression is about quality or prediction. Partially yes, but can you improve this further? Okay, so in case of classification and regression, we are trying to predict a variable, but in classification, the variable is discrete, whereas in regression, the variable we are trying to predict is a real number. Okay, it is not discrete, it is continuous. Now, if I give you a concrete example of this, okay, let's suppose you want to make a system, any machine learning system. Okay, we are not talking about ANN, it could be anything, in which you feed some data, like how many hours you study, what is your attendance, how many hours you prepare for quizzes, and so on. And if this system is predicting your grade, okay, we say there are 4 possible grades, A, B, C, D. Okay, so you see there are only 5 possible grades. So this is an example of classification because your output is discrete. There are 5 labels or 5 classes, and the system will predict one of these. Okay, so the variable you are trying to predict is discrete. It is either A or B or C or D or F. On the other hand, if I slightly change this problem, I say, okay, this is your machine learning system. You feed it the same data, how many hours you study, how many assignments you did, how many hours you prepare for a quiz, and you ask this system to predict your GPA. Okay, then this is a real number. Okay, it can have any value in an interval. For example, in this case, it can have a value in the interval 0 to 4. Okay, so this is an example of regression. This is an example of classification. Very similar example, but what you are predicting actually changes the whole idea, whether you are doing classification or regression. Okay, so in simple words, the best answer could be that in regression, the variable we are trying to predict is continuous. In classification, it is discrete. Okay, then after these are two general terms. Okay, then comes the question. There is another terminology which is called logistic regression. So can anyone tell me what is this logistic regression? Or let's make it simple. Logistic regression goes here or here. Okay, you can just tell me whether it goes to the classification part or the regression part. So logistic regression, don't be misled by the terminology regression. Okay, for historical reason we have this name. So logistic regression is actually a classification task, and more specifically logistic regression is a two-class classification problem. Okay, means there are only 2 classes, 0 or 1. So if you see all the examples that we have seen today, almost all the examples, we have been solving two class classification problem. Okay, all the gates, they were two class, 0 and 1, they were two outputs. Then at the end, I showed you an example of buying a car. So whether you buy a car or you don't buy a car, you only have two classes, yes or no. Okay. Similarly, if I show you an image to the system, okay, and I ask, okay, whether this image has a human or not, human present or not. So it will give me a probability that maybe it is 90% sure that there is a human, or it can give me a probability which is low that there is no human. So again, there are only two classes: human is present in the image or human is not present in the image. So you see, this is something that we call logistic regression. So I'll just quickly introduce this, because in order to implement logistic regression, we don't need any new concept. Whatever we have seen, the same machinery we can use. We have just given that a fancy name. Otherwise, you have already seen this logistic regression in the previous examples that we have been discussing today. Okay, so let's just make it a bit formal and change the example. Instead of dealing with gates which you did not like much, or pass the course or do not pass the course, we change it problem, that okay, an image is shown to the system and the system has to tell whether there's a cat or there's no cat. Okay, so it means if there's a cat, we expect the system to output 1. If there's no cat, we want the system to output 0. Okay, so now you see, these are possible labels. There are two possible labels. Now there is another important thing, that in the previous examples, the data that we have been feeding to the perceptron, we only had two inputs, x1 and x2. Okay, and we were getting an output, and I had written an equation for this, and that was an equation of a straight line. Okay, if you change the weights, this line will change position or slope, whatever. Okay, but you see, every time I will not have only two inputs. Suppose I have three inputs. What will happen then? It means that now I will have an expression like this, maybe 4 minus 2x1 plus 3x2 minus 6x3. It would be something like this. Okay, so now it means I have three variables. I don't have two variables. So I am in a three-dimensional space: x1, x2, and x3. So when we are talking about two features or two inputs, then my decision boundary is a straight line. But what if I have three inputs? So you see, when I'm in a three-dimensional space, and just like your room in which you are sitting, and suppose I ask you to divide your room into two parts, what will you do? You cannot divide your room into two parts using a bar or a thread. You need a wall, and formally, actually, you need a plane. Plane is like, you have seen cardboard or a ply sheet which is very thin. So mathematically, the thickness of a plane is 0. So you see, if you imagine that you are in a room and I ask you to divide your room into two parts, so you need a cardboard sort of thing, or a wall, a thin wall, which will actually divide it. You cannot divide your room into two parts by a straight line. And mathematically, that thing is called a plane. Okay, if you are talking about three inputs. And if you have, say, multiple inputs, like n inputs, then we'll call it a hyperplane. Okay, but the important thing is that it will be linear, right? When you are talking about this expression, no matter how many variables I have, I never have a term like this, x1 square or x1 cube or something. So irrespective of the fact whether I have two inputs or three inputs or maybe k inputs, I will call it line or plane or hyperplane. But all of these are linear, means there is no curve involved. So it means when I ask you to divide the room using a plane, plane is something which is straight. You cannot curve the wall or the cardboard, whatever you are calling it, right? So this is basically the generalization of logistic regression, because every time we will not have two inputs, we can have more than two inputs. But the important point is that the decision surface would always be linear. It will never be curved, because you will never have a term which is like x square or x cube or so on, right? So you have already implemented it. It's just another notation, right? That you see, we have x, and now x is not two-dimensional. X can be n-dimensional, means x can be 3 values, 4 values, 5 values, and so on, right? So this is our input x, right? Suppose maybe instead of 1, I have like n is 100, so I have 100 values, and then If I have 100 inputs, I will have 100 weights to learn. For every X, I will have a weight, right? So if I have N inputs, I will have N different weights to learn. And plus, I will also need to learn another value, which is called bias. Okay. So you just saw in a perceptron what actually happened. This is just a different notation, a vector notation, that instead of writing summation, I have just said W transpose X, which is the same thing as W1 X1 plus W2 X2 and so on up to Wn Xn. Okay, so you compute this, you add bias, you apply activation function. But now what has changed here, as I told you, instead of a step activation function, now we are using sigmoid activation function. So what it will do is, it will give you not only 0 or 1, it will give you a value in between. Maybe it will give you value 0.5 or 0.7 or 0.9, and now you can treat it as a probability. Okay, for example, if it gives you 0.8, so it means it is 80% sure that the image you have shown to the system, it actually contains a cat. Okay, so it's the same thing. Okay, and just maybe I'll conclude by showing you few, you can say, illustrations, and then we'll discuss this next time, right? So we are actually using this model, which is logistic regression, or which is simple perceptron. But the only thing we have changed is that instead of a step function, now we are using a sigmoid function, and we can have any number of inputs. Okay, but since I'll be visualizing, I'll be plotting some data, so that's why I have plotted the data in 2-dimensional space, right? Because maximum I can plot is 3-dimensional, but it will be difficult for you to visualize. Okay, so you see we have two classes. Blue one is say 1 and red one is 0. And visually, it seems like that I can draw a straight line which can separate these two classes. Okay, so it means I generate some random data and I try to solve this problem with logistic regression. Okay, and logistic regression is the same thing that we have discussed. It will give you a straight line as a decision boundary. Okay, so you see, this is some code I'll quickly walk through, but objective is not to explain you syntax of the code. Okay, I'm just explaining you at a high level that what is it doing. Basically, whenever you have to make a model in TensorFlow, you have this API which is called sequential. Sequential means that in a sequence you will keep on adding layers. Okay, so presently what are we implementing? We are implementing this. Okay, we have only 2 inputs, and this is a single neuron we are implementing. Okay, so when we say dense is a layer which is used in neural networks, right? But for the time being, I don't have any layer, I just have only one single neuron, right? So I will discuss it more once we are making a deeper network, right? Units 1 means that I only have one neuron here. If I need multiple neurons, 3 neuron, I'll put 3 here. Okay, input is 2 because I have 2 inputs, and the activation function is sigmoid. Okay, so I, with this statement, to a model, I have added one layer, which is this one, in which I have one single neuron, because I am doing logistic regression, I need only one neuron. Okay, and this statement is actually equivalent to this, what you see visually. Okay, then you can actually train this. By training, we means you are trying to learn the weights. And you just saw a comprehensive example. How do we learn the weights? We initialize randomly, and then they keep on changing, and eventually after certain epochs, you learn the weights. So if you are implementing something, you just call this function fit. This is doing all that W1, W2, it will keep on doing. And you see, you were asking how to stop. So this is the maximum number of epochs we have given. Okay. So anyways, I'll just quickly go to the output, that if you run this program, so it will give you something like this. Okay, since it is sigmoid, so you see in this region, it is very sure that this is class 1. In this region, it is very sure that this is class 0. And this is the region where the probability is between 0 and 1, right? Because the network is not very sure, not network, just a single neuron, right? For example, for all of these, maybe the probability is like 0.7. Here the probability, instead of 0, maybe it is 0.2. Okay, and maybe this is the confusing part, right? Because even if I draw a straight line at 0.5, so some of the points are very close to the decision boundary. So if a point is very close to the decision boundary, your algorithm is not very confident, right? So it will give you, in this region, it will give you values like 0.5, 0.6, means it is not very sure. On the other hand, if your value is close to 1, maybe for all of these points, your algorithm would be very sure that they belong to class 1. For these points, your algorithm is very sure that they belong to class 0, right? So this is just a visual illustration of how it works with a single perceptron. Okay, we'll continue this discussion next time, and maybe we can spare the last few minutes for some